I'd like to just discuss this. I know it is actually with the greenhouse effect, and we haven't actually looked at it as yet in the curriculum. It'll be in Unit 8. Describe what is meant by a greenhouse gas. This is a gas that absorbs energy, usually reflected energy from the surface of the Earth. But I just want to look at this question in more detail. So you've got the electromagnetic radiation of frequency 9.1 times 10 to the 13 hertz is the infrared region of the electromagnetic spectrum. So this is actually light that is actually re-emitted from the Earth in the forms of heat. Now, we can see that before we actually worked out that the natural frequency, or the frequency of this hydrogen atom as it vibrates, was also equal to this 9.1. So this is actually the natural frequency of the methane, which is the C4H molecule. And so what happens is that this infrared radiation, because it's also got this natural frequency, the methane, the CH4, will readily absorb it, and because you would get resonance occurring, in that natural frequency is the same as this frequency here, and so it will be working together, and it will cause a large increase in the to and fro motion. The amplitude is going to increase, and because of that, the speed will increase, and because temperature is proportional to the average kinetic energy, to the EK of those molecules, your temperature is going to increase, so that causes a warming effect. Okay, so let's go on to this next question, question 12. So it says, by reference to the energy of a traveling wave, state what is meant by a ray. Okay, well, a ray gives the direction in which the energy is traveling. So you may have water waves that are going in this direction, so they are transferring energy, and we would draw a ray in that direction. This would be your ray. We usually always draw them at 90 degrees to your, what we call your wave front. These over here are your wave front, and this is your ray. So these are the things, these are your crests going, and they are moving across in the direction of that ray. The wave speed is the speed at which the energy is being transferred, because remember, we have to do it in turn by reference to the energy. So the speed at which the energy the energy is being transferred. All right, good. So there's our base there. Going down to this next part, it's over here. Let me just get out of there. Here we go. We actually given two graphs here. It says over here, the graph below shows the variation with time t of the displacement xa, wave A, as it passes through point P, and we get the same for wave B. So we've got two waves, they're moving through, they are going and obviously they've got a different period, different frequency. Alright, so we have to calculate the frequency of the waves. So we can calculate from this, we see that one occurs in 6 milliseconds. Now notice this, we've got millimeters, milliseconds, so we've got to be careful with these. A milli is times 10 to the negative 3. So our frequency for this for wave A is going to be the frequency is 1 over t, so it's going to be 1 over 6 times 10 to the negative 3 seconds, and that gives you about 170 hertz. Okay, again, I'm doing it you see you've got two significant figures, so we've got our two significant figures there. And it's the same here for wave B, because also 6 seconds is for one full wave. But notice that these waves are really out of phase by a certain amount. So here you've got a crest, and here you've got it at the equilibrium position. So they partially are out of phase. Okay, now just going down here a bit further on. It also wants us to, over here, it says the wave passes simultaneously through a point P. Use the graphs to determine the resultant displacement at point P of the waves at time 1 millisecond and 8 milliseconds. So I'm going to do this up here where the graph is actually, so we can actually see it on the graph. So let me just pull this up here. So we're looking at 1 millisecond, and we are looking at 8 milliseconds. So let's start off with 1 millisecond. This is over here. So for this at 1 millisecond, I'm over there. You can see that our height, now just be careful with this, we've got 5 little small, so each of these is 2, so I'm about 1.7 millimeters there, and here at 1 millisecond I am over here, well, I'm over there. You're about 0.7 millimeters. So what's going to happen is that you're going to get, at that point, you're going to have this one, which is 0.7 millimeters, and this one you're going to get 1.7. So you're going to get your 0.7 and your 1.7, and they're going to add up to the total of 2.4 millimeters. That would be for your 1 millisecond, your 1 millisecond time. Good, let's have a look now at the 8. When we were at 8. Now here at 8 we are for this wave A, we're over there, and so we like over there. We are about 1.7. So for A we are about 1.7. This is for A millimeters, and for 8 we're now down over here. So there we are at about minus 0.7 minus. So we've got this over here, minus 0.7. And when we do the algebraic adding together, this is going to be, you're going to get 1.0 millimeters coming out there. So your answer would be 1 point. So there you're getting your constructive. In the first case, you're getting some constructive interference, and here you're getting some destructive interference. You're getting a lowering of the total wave. Okay, thank you.